4.5 Linear Approximations and Differentials. In Part 2, we will focus on differentials. Recall that the linear approximation of f at A is just the tangent line of f at A. And if you have points near A, the tangent line does a very good job at approximating the function. Let's move a little bit away from our point A. Let's move a distance of delta x. The small movement of delta x in the horizontal direction causes a vertical change in the function, which can be approximated by a vertical change in the linear approximation. Let's find that change in the linear approximation. Notice that the tangent line and the function have the same height at the point of tangency. We're going to use that in a little bit. Now let's focus on L of A plus delta x, and we're going to use the linear approximation formula. Instead of x, use A plus delta x, and then just clean it up. If we throw in the idea that L of A equals F of A, then that will tell us the vertical change in the linear approximation. All you need to do is just clean up the right-hand side of that bottom equation. The small movement of delta x in the horizontal direction causes a vertical change in the function, which is approximated by the linear vertical change, which we just found to be the slope of the function at A times that little movement of delta x. So we've got our actual change and our approximate change that we found using linear approximations. So we have a small movement of delta x in the horizontal direction causing a vertical change in the function, which can be approximated by f prime of A delta x. I would like you to notice that this is consistent with our knowledge that average velocity is approximately equal to instantaneous velocity as long as our horizontal change is small enough. Now here's a rather ugly graph for you. What I want you to zero in on is the actual change in height and the approximate change of height. You can see that we need delta x to be very small for one to be able to approximate the other. All right, let's do a problem. Let's approximate the change in this function when x changes from 1 to 1.05. If you're starting at 1, then A is equal to 1. If you're ending up at 1.05, then your delta x is 0.05. Now our function is just given by x to the 9th minus 2x plus 1. Okay, what do we need to do? We need to find the derivative of the function. We need to find the derivative of the function evaluated at A. And we need to put all of this into our formula. So what is the derivative of the function? What is the derivative of the function at 1? Oh, the derivative's pretty easy for us by now, and its evaluation is 7. Plug this into our formula, and we get that the actual change in height is about 0.35. When x changes from 1 to 1.05, the function increases approximately 0.35 units. Approximate the change in the surface area of a hot air balloon when the radius decreases from 4 meters to 3.9 meters. Since the surface area of a sphere is given by 4 pi times the square of the radius, let's let x be the radius. Then our function, our surface area function, is 4 pi x squared. Our starting point is 4 meters, and we're going down to 3.9. So delta x is negative 0.1. We need to find f prime of a delta x, or f prime of 4 times negative 0.1. All right, let's find the derivative and evaluate the derivative at 4. Put all of this into our function. And put all of this into our formula, and we get about negative 10.05. When the radius of a hot air balloon decreases from 4 meters down to 3.9 meters, there's an approximate decrease of 10.05 square meters in the surface area of the hot air balloon. All right, here's a little summary for you. To approximate the function near a given point A, use the linear approximation. To approximate the change in vertical direction in the dependent variable when x changes from a to a plus delta x, use the formula f prime of a delta x. Here's a definition for you. Definition of a differential. It's a new term, differential. Now, x is our independent variable, and the differential of x is just dx. And the corresponding change we're going to call, we call delta y, which is approximated by what we're now calling the differential dy. Wow, what does all this say? Let me see if I can say that again for you. We define dx to be delta x and dy to be f prime of x dx. These are just definitions. Then, if delta x is small, the actual change in height is about equal to the differential dy. Let's use this new notation to write the approximate change in this function given a small change dx. First, let's rewrite the function so that it's easier to find the derivative, and then use the chain rule. Take the derivative and use the double angle formula. So the differential is just dy equals negative 3 sine of 2x times dx. And that's how you find a differential. Just take the derivative, clean it up, and then attach on that small horizontal change dx. And that is the differential dy, which approximates your vertical change. Take care. Let me know if you have any questions.